Welcome back, Physical Science 20. This is the 5.1 booklet, the Combustion of Hydrocarbons. So we'll take a look at it, but this is a fairly easy and straightforward one, so hopefully it'll be no issue. So here it talks about carbon monoxide poisoning at a Vancouver Canucks game. And then it leads into what combustion is. So it's a reaction which fuel burns, and it has to be in the presence of oxygen, and usually that oxygen is pulled directly from the air. Coal, propane, gas are common fuels. The molecules of fuels, like all compounds, are a source of chemical energy, so the breaking of bonds to release the energy. Combustion releases the chemical energy as thermal energy and light. The other products vary depending upon the type of combustion it is. So in all of them we have carbon dioxide and water, and whether it's incomplete or complete, we may have carbon monoxide and also carbon. And of course, another fact here is that carbon dioxide is a greenhouse gas, and it contributes to climate change, as does water vapor. Propane, for example, from your barbecue, is an organic compound, a molecular compound containing one or more carbon-carbon bonds. So carbons attached to carbons are organic compounds. Many organic compounds also contain one or more carbon-hydrogen bonds. Many fuels contain impurities such as sulfur compounds, heavy metals, etc. Combustion releases these substances into the atmosphere as air pollution, and of course, unless they are removed by some pollution control technology. Okay, so fairly straightforward with that first page. Many substances burn. There's a special group of organic compounds called hydrocarbons, and yes, as you've guessed it, they're made up of hydrogen and carbons. So for example, propane in your barbecue, C3H8, you can see there's 3 atoms of carbon for every 8 atoms of hydrogen. Butane from a lighter, 4 carbons to 8 hydrogens. Gasoline is a mixture of mostly liquid hydrocarbons. Most hydrocarbons are extracted from coal, oil, and natural gas. Although some hydrocarbons are used in the synthesis of other compounds, most are burned for their energy content. Okay, types of hydrocarbon combustion. So looking at this, all hydrocarbons burn provided that they are hot enough and have enough oxygen. Oxygen is the key. It's the other reactant that is required to have a combustion. So we can have either a complete combustion or an incomplete. Complete combustion means that oxygen is plentiful. You have more than enough of it. The products, in the case of a complete combustion, CO2, carbon dioxide, and water. And of course, energy being released as well. So those are always the products for a complete combustion. Sufficient oxygen in order to have the correct ratio of hydrocarbon to oxygen. And of course it has CXHY, because depending upon the hydrocarbon, the X and Y are different numbers, of course. So for example, methane gas from the burners in the chemistry lab, CH4 plus 2O2, and you can see CO2 and H2O. So we need to have more than enough oxygen available. Complete combustion is the ideal way to burn a fuel because it releases the most energy from the fuel molecule. As a result, complete combustion produces the cleanest and least sooty, so none of the black smoke, etc., which we consider to be carbon, and also the hottest flame. And if you ever used a Bunsen burner, that's a blue flame is an indicator that complete combustion is happening. In other words, we have more than enough oxygen. And of course here, keeping a gas furnace well maintained ensures that the gas is burned completely as possible, produces the most energy, reduces cost, and of course does not result in the soot being released, less carbon monoxide, etc. Ethine, also commonly known as acetylene, is also a good example here. If it burns with a good supply of oxygen, it generates a high enough temperature needed to cut steel. And of course, an oxyacetylene torch is supplied by 2 gas cylinders, one containing the acetylene, the other containing oxygen. And of course, you can adjust the amount of oxygen you need depending upon what process you're doing. Okay, so complete combustion, having more than enough oxygen and producing the cleanest products. If you look at incomplete combustion, the supply of oxygen is limited. So this situation can occur while burning a hydrocarbon in an enclosed space. When operating a car or barbecue in a garage, for example, incomplete combustion often occurs in less than ideal conditions. Incomplete combustion is said to be fuel rich. So what we could realize is happening there is that the fuel is not being released as sufficiently as it could. It contains still all the energy because we don't have enough oxygen. A log in a wood-burning stove is an example of a fuel-rich condition. There's lots of fuel, but limited oxygen. The lack of oxygen prevents ideal or complete combustion from occurring, limiting the quantity of energy released. Flames resulting from incomplete combustion are yellow color, sooty, meaning that black smoke there, and of course cooler than if it were a complete combustion, which in that case is a nice blue flame. Incomplete combustion is usually undesirable, however it can be useful in some applications. For example, incomplete combustion is used to start gasoline-powered devices such as lawnmowers. A cold lawnmower is much easier to start if a fuel-rich mixture enters its engine than if there's less fuel and more air. The volume of air entering the engine is controlled by a valve called the choke. Before starting a cold lawnmower, adjust the choke so that it is in the closed position. This restricts the airflow, and which results in a fuel-rich mixture which is easier to ignite. So easier to ignite a fuel-rich mixture even though it results in incomplete combustion. Once the engine starts, you might see sooty exhaust being produced, so black smoke. This is evidence of an incomplete combustion. After warming up the lawnmower a few seconds, open the choke, allowing more air to mix, and that would result in more complete combustion. Okay, so incomplete combustion produces a variety of combustion products than complete. Carbon dioxide, water, and energy are produced just like in the complete combustion, but you have extra things. Carbon monoxide, or soot, or both, and by soot we use the chemical symbol C for carbon. So incomplete combustion it depends upon the circumstance. You'd have to have some more indication as to what is being produced in order to completely describe an incomplete combustion. So for example, here is an incomplete combustion here. So C7H6 plus 7O2 releasing 3 carbons plus 2 carbon monoxides plus 2 carbon dioxides and water. Whereas here we have a complete combustion here. So I actually have this as an error here. It should be complete. So there's only one chemical equation for the complete. Actually, it did say that this was an incomplete combustion here as well, even though there isn't any. Well, I guess yes, there is a carbon monoxide there, so yes, that would be an indicator of an incomplete combustion. But as you can see, there's no CO2 being released here. So again, it's kind of hard to predict what it will be. But a complete combustion, there's only one way. There has to be CO2 and there has to be H2O only with energy. Note that more oxygen molecules are required per molecule of heptane for complete combustion. So here you need to have 11, here we have 7. Here we have 11, but for whatever reason it results in incomplete. Concerns related to incomplete combustion. Of course, enclosed spaces where there's poor ventilation can lead to a lot of issues. Even candles in places of worship can have a number of health concerns. So if we look at a couple of these, a portion of the energy being obtained from it, we only get a little bit of energy. We don't get all of the energy that we could out of the fuel or the reactants. However, the combustion of gasoline is more complete while traveling at the highway speeds and when driving in the city. The most incomplete combustion of gasoline occurs when it's idling. This is because an idling engine operates at a lower than optimal temperature. As a result, gas burns less completely when the engine operates at higher temperatures. Also, fuel residue may form on the engine components, making them work less efficiently and breaking down that much quicker. Soot particles from incomplete combustion are an inhalation hazard. Many of the chemicals in soot are toxic. Furthermore, soot particles are often too small to be filtered by your respiratory tract. As a result, these particles may penetrate deep into your lungs and irritate sensitive tissue. This can lead to respiratory problems, including asthma. Soot can also foul moving engine parts, making the engine less efficient. And of course, last one here, carbon monoxide. That's toxic, silent killer, no taste, no odor. so it can kill you, etc. If you're inhaling a lot of that. Other hazards. Talks about firefighting here, and since we live in a world with more and more plastics and synthetic compounds, when those things catch on fire, there's a lot of toxic gases that get released and are extremely dangerous. So if you want, like for the career section, firefighting, you could include that in the physical science course, because there's a definite link there. Even natural substances can produce potentially hazard chemicals when they burn. For example, vegetations, certain forms. There could be hazards associated with that as well. Okay, so summary, recall hydrocarbons contain hydrogen and carbon. The combustion of hydrocarbons is either complete or incomplete. Complete combustion occurs when you have the most oxygen present. It releases the most energy and has the cleanest flame. The general form looks like this, in which we have CO2, H2O, and energy being released. Incomplete combustion, it's when we have limited supplies of oxygen, and we could have CO2 and H2O in addition to carbon and also carbon monoxide. And incomplete combustion, it's somewhat difficult. You'd have to have some indication as to what the formula is. Okay, so the questions I would like you to do are 1, 2, 3, 4, 5, 6, 7, 8. That's it, so just 1 to 8. If you wanted to look here, though, for research later on in the course, there's some indications. So paintings, how come they get blackened a little bit or darkened? Issues involving cars, the idling versus driving, etc. You may wish to look at those. And also here, cancer versus chemical exposure. That's another interesting one to research as well. But for now, questions 1 to 8 is what I'm looking for 5.1. Okay, see you soon.